quasars, particularly on their X-ray variability. And I'll discuss how accretion disk winds may be responsible for driving much of this behavior. And I've done this work with several excellent colleagues. In particular, I want to highlight the efforts of Bin Luo, who is a former student of mine, who's now a professor in Nanjing, and Qingling Ni, who recently graduated from Penn State. And these weak-line quasars have been discovered in significant numbers in recent years by large optical spectroscopic surveys like the Sloan Digital Sky Survey. We have now found about 400 of these weak-line quasars, and they are notable from their name as for having these remarkably weak lines. There have been a variety of different criteria that have been used to define these weak-line quasars. Today, I will be generally focusing on those that have very weak rest frame ultraviolet lines like carbon-4 and Lyman alpha. These are radio quiet, blue, luminous type 1 quasars. Some of the most luminous quasars in the universe, I'll show you an example in just a minute, are these weak-line quasars. And not only are they exceptional in terms of their weak lines, but the lines often also show large blue shifts. Here is a plot that shows the rest frame equivalent widths versus the carbon-4 blue shifts for the quasar population. General Sloan quasars are located over here in this part of the diagram, and the weak-line quasars are located obviously having very weak lines and with line blue shifts of, well, sometimes thousands of kilometers per second. In the most extreme cases, we have line blue shifts approaching 10,000 kilometers per second. So in these systems, it appears that the broadline region may be in some kind of an extraordinary outflow. And of course, in this diagram, people who study eigenvector 1 and related correlations have suggested that as you move in kind of this direction in this diagram, you are likely moving toward high-Eddington ratios. And I'll have more to say about that in just a little bit. Here is an example just showing you a spectrum in detail of one of these weak-line quasars. This is probably my personal favorite. This is an extraordinarily luminous quasar, has an MI of -30.2, was found by Sloan. It's a redshift 2.2. And you can see, for example, look at the carbon-4 line here. It's totally shifted from where you would expect carbon-4 to be, whereas magnesium-2 and so on are more normal. And in fact, we've defined the redshift for this particular system based on rest frame optical spectroscopy. And you can see carbon-4 just totally shifted from where it should be. So that's the extraordinary nature of the line blue shifts, indicating again that perhaps the broad line emitting region is in some kind of an outflow. Now, we have been investigating the X-ray properties of these weak-line quasars. We have now observed about 65 of these luminous weak-line quasars, typically with Chandra snapshot observations. So we're doing fairly short observations, trying to define the basic X-ray properties. And I have 3 slides here where I'm just going to highlight the remarkable X-ray properties we find for these systems. But the first point I want to make is that about half of the weak-line quasars are notably X-ray weak compared to what you would expect for a typical quasar. This plot here shows alpha OX versus the 2500 angstrom luminosity. And these sources here are X-ray weak by large factors, by factors of 10, 20, 30, 50, sometimes more, compared to what you would expect for a typical quasar of that luminosity. This plot here shows the alpha OX parameter taking out its luminosity dependence. The weak-line quasars are shown in blue, and these are you can see how the population is shifted toward X-ray weak values. Now, an important point I do want to make, however, is they're not all X-ray weak. Note that there are X-ray weak weak-line quasars and X-ray normal weak-line quasars. And I think that's an important clue to understanding these systems, and one that I will return to. Secondly, in terms of X-ray properties, if you look at the X-ray weak half of the population, well, they're hard to constrain in detail because they're X-ray weak. You don't have lots of counts to work with. But on average, when we look at our sample of X-ray weak systems and we stack their X-ray spectra, the data indicate hard average X-ray spectra with effective power law photon indices of like 1.2 to 1.4. The natural interpretation there is that there is some kind of heavy X-ray absorption, at least often present in these systems, likely with some kind of partial covering and or Compton reflection coming into play. We do have one case, that extraordinarily luminous one I just told you about, where we have a modest quality X-ray spectrum shown here, and it also indicates just from direct spectral fitting that the presence of substantial X-ray absorption. We can't constrain it very well, but the typical power law photon index for this system, just individually fit, is about 0.6. And the suggestion is that you have a lot of absorption present and likely a lot of Compton reflection coming into play that is shaping the X-ray spectrum. So that's point number 2. Point number 3 is if you look at the X-ray normal part of the population, they have normal power law X-ray spectra as expected for quasars. However, the power laws are quite steep. We have both, again, performed joint Chandra spectral fitting of 17 normal weak-line quasars, and we have performed XMM Newton analyses of samples of these weak-line quasars, and we consistently find these things have very steep power law spectra, and that, of course, has been found to indicate a high Eddington fraction, consistent with the suggestions that we had from the line properties that these systems may have high Eddington ratios. So those are the observed facts, and all those observed facts have led us to a toy model that I want to describe, and I will then also highlight the disk wind connections to all of this. So in terms of the high Eddington ratios, well, high Eddington ratios are expected generally to lead to thick inner accretion disks. And here are 2 examples of papers. Of course, there are the long-known slim accretion disks, and now people are performing quite sophisticated global magnetohydrodynamical simulations, and they generally find that the accretion disk becomes quite thick when you run a system at a high Eddington ratio. And such high Eddington ratio accretion is also generally expected to launch fast wide-angle disk winds, as shown here, and as also was found in such simulations. And so all of that together has led us to a toy model, is what I call it, for these systems, where we propose that there is an inner accretion disk that is thick with a substantial outflow present in these weak-line quasars. And this can explain, we believe, in a simple and unified manner, the weak lines. The idea there is that the thick inner accretion disk prevents ionizing radiation from effectively reaching the high ionization broadline region. And the high ionization lines are the ones that are most notably weak in these systems. Of course, here, the high ionization broadline region, that has to be fairly equatorial, and that is at least consistent with much of the data. Furthermore, this can explain the diverse X-ray properties, kind of in a similar way to the unified model. The idea here is that the X-ray weak systems would be ones where you're viewing the system in a quite equatorial manner, and where the X-rays are prevented from reaching your line of sight due to blockage by the thick inner disk. Whereas the X-ray normal systems could be explained when you're observing them in a much more polar manner. And so it's just an orientation-based unification scheme, although it's happening on a vastly smaller scale than the normal torus-based unification scheme. And of course, note in both cases, the lines would be weak. And so this can explain, as I mentioned, both the X-ray weak and the X-ray normal weak-line quasars. And moreover, this model is successful at explaining at least some of their other multi-wavelength properties, and you can see the papers for our discussion of that. I will also, of course, note that this type of a model, this thick inner disk type model, has also been put forward to explain some of the diversity of the properties of tidal disruption events in this paper, for example, as well as in ultra-luminous X-ray sources. And so we're talking about the kind of quasar version of these ideas. I will also mention that this model may have, and these sources may have broader relevance in sort of illuminating other more general processes relevant to understanding quasars. For example, we have suggested that perhaps the disk and outflow thickness plays a significant role as a driver, for example, the Baldwin effect, which of course has now been shown largely to be probably a Eddington ratio driven effect. And the idea here would be that accretion disks progressively thicken as you move along here, and ionizing radiation is progressively prevented from reaching the broadline region as this thickens, and that might be able to explain this correlation. I'm not sure that's the case, but at least that's an interesting thing to think about. Okay, so then now I want to get on to the extreme X-ray variability. So we have been working hard over the past couple of years to get to perform a uniform sensitive X-ray survey of a sample of 32 representative weak-line quasars. These systems were found originally in small numbers. People just started doing ad hoc pot shots at them, but there wasn't really a high quality, uniformly observed sample. And that's what we're trying to do with this sample of 32. And this is in a paper that we're currently working on, led by Qingling. And this has required reobserving with Chandra some weak-line quasars to tighten up their X-ray upper limits. We had some that weren't X-ray detected, but the limits were not as tight as we would have liked, so we're making them more sensitive. And these plots that I showed earlier in the talk are in fact coming from this uniform sample. So let's just define their properties in a fairly representative manner. And we were surprised when we had reobserved one of these weak-line quasars to find that it had exhibited a dramatic flux rise. This is the system, it's J1539. Back in 2013, we had observed it in a Chandra snapshot, and it was totally undetected, quite X-ray weak. And here it was in 2013 compared to a typical quasar SED. It was notably X-ray weak. We then found when we observed it in 2019 September that it had changed from being X-ray weak to X-ray normal. It rose up by about a factor of 20 in flux, okay, and became quite X-ray bright. And to our ability to measure its X-ray spectrum, which clearly is very limited because this was a very short observation, it appeared to have a fairly typical X-ray power law, although again, the uncertainties are large. And note, this is an extremely luminous quasar, has an MI of minus 28, so it's nothing to sneeze at, indicating that, there's an enormous amount of power wrapped up in this system. And this type of variability, particularly among highly luminous quasars, is very rare. In fact, we have systematically, by mining the Chandra archive, have constrained how often X-ray variability of a certain amplitude is. And that's what this plot is showing. This is showing X, which is basically the log 10 of the count flux ratio between two Chandra observations, split up as a function of time scale and as a function of luminosity. And J1539 would have an X parameter, as we define it here, of like 1.3. So it's way off in the tail here. And such events are extraordinarily rare among luminous quasars. Now, as soon as we found that this X-ray event, thankfully, we were analyzing our data the day it was coming in, and we immediately pounced on it and got follow-up optical spectroscopy. And we performed the spectroscopy with the Hobby telescope, which Penn State has a significant stake in. And the emission lines remained weak, and the UV continuum was largely unchanged, despite the dramatic X-ray variability. The HET spectrum is the one here kind of in dark gray. And you can see the emission lines are clearly still weak, and the UV continuum has not changed dramatically. And so it's the X-rays that are changing by large amounts without large changes, for example, in the emission line properties or in the ultraviolet. And I will also note that now we actually also proposed an additional Chandra directors to expressionary time observation. The source, when we were able to reobserve it with Chandra DDT time, has returned now to being X-ray weak. So it went way up and got weak again. We don't, of course, know characteristic time scales because of the very limited sampling, but it's a remarkable thing. And again, the HET showed no material UV variability, despite this large variation as well. So what could be the possible drivers of this variability? Well, we have suggested that the variability can be understood in the context of the model that I described to you. For example, this inner accretion disk is expected to be rotating very rapidly because we're down on quite small scales here. You could actually have substantial rotation of the thick inner disk and its outflow. And if the disk, and particularly if the outflow were azimuthally asymmetric, and the simulations indicate that this outflow quite likely is quite azimuthally asymmetric, you could imagine going from periods when you have quite heavy X-ray obscuration to periods when you don't, particularly if your line of sight is arranged so that you're just somehow skimming part of this wind. Or alternatively, another possibility is the wind itself, of course, is moving at high speeds. You could have changes in the clumpy outflow itself leading to these types of variations. We can't discriminate which of these is the case, but we think quite likely wind variations have something to do with this. Now, of course, I want to point out that when we thought about this, there is another source studied by Giovanni Minuti, PHL 1092, which has also shown this type of extreme X-ray variability. This is also a weak-line quasar. It's a redshift of 0.39. And this source has been observed, well, many times now over the years, but particularly it was discovered to have large X-ray variations with XMM Newton. And it varied by a factor of like 260 between X-ray weak and X-ray normal states. And so this, of course, triggered our attention. We have this one event that we found, which was, of course, extraordinarily rare. Of course, the only other event we know of that has similar extreme variability is another weak-line quasar. So, of course, this is led us to suspect that perhaps weak-line quasars preferentially show such extreme X-ray variability. And we, in fact, are now trying to test this. We put in a Chandra multi-cycle observing proposal for Chandra cycles 23 to 25. And we are aiming, by observing 10 weak-line quasars once per year over 3 years with Chandra, to derive the first systematic constraints on X-ray variability for weak-line quasars. And this will let us assess quantitatively, is the X-ray variability among weak-line quasars indeed somehow enhanced? Are these extreme X-ray variability events preferentially occurring among the weak-line quasars? We're going to try to address that systematically. And we will, of course, also be re-observing them with the HET to get systematic optical spectroscopy each time there's a Chandra observation. I also want to point, just to end, because I see I'm getting probably short on time, that we have found in our data mining through the Chandra archive, we have serendipitously observed, and we have discovered in serendipitous observations another weak-line quasar now that has shown strong fast X-ray variability. Of course, as soon as we found this event and saw a hint of this pattern, we started mining the Chandra data for all of the weak-line quasars. And there is another source shown here, another extremely luminous quasar. That's a weak-line quasar. You can see that here, where the flux in this case dropped by a factor of 7.6, and it did that within just 2 days, which is quite remarkable. And you can see that here. So there were 3 Chandra observations available for this source. There was one back in 2015, and then there were 2 more obtained, well, on March 27th and April 3rd. And you can see the source varied just on that short time scale between the yellow points and the green points, varied from being X-ray bright and having a fairly softish X-ray spectrum to X-ray faint and having a hard X-ray spectrum. And again, it did that within 2 days. And our best estimate of gamma, and again, the counts are limited, but our best estimates of gamma, power law photon index, is that vary between 2.3 and 0.9, again, just within a couple of days. And so we have suggested, again, this may be a kind of eclipse event in the system. And the notable thing is that this, again, is a very luminous quasar. We estimate its black hole mass to be 6 billion solar masses, and you require relativistic motion at a good fraction of the speed of light just to get an eclipsing material across a corona, even if you take the corona to be quite compact, to say have a size of 5 gravitational radii, you require quite high velocities. So this is another remarkable system. Here's our little schematic for this system. There were, again, were 3 epochs. So first we found it to be highly obscured. Then 58 days later in the rest frame, it was, as far as we could tell, fairly unobscured. And then just 1.9 days later, it had returned to being obscured. And so these events may be quite rapid. Again, the data are very limited. We're hoping to get better constraints, and our overall aim, again, is to test the disk wind model, see if it can drive this extreme X-ray variability, and then come to understand another aspect of these remarkable weak-line quasars better. And I'll wrap up there. Thank you very much.
Thank you, Niel. Okay, questions we'll do from the floor first. Anyone other than Chris? Off you go, Chris.
Hey, good morning.